All right, I thought I would provide you with a tutorial for the first exercise in your lab manual, mainly because it involves some math and a rate problem, and we're going to be doing these types of problems in other lab exercises in the future. So as a refresher for perhaps some of you that need it, I hope that this will be beneficial. We want to recognize that this is a rate problem, and in geology we work with rates a lot. So let's review that. Rate equals distance divided by time. And we are going to need to figure out our distance and our time in order to solve this problem. First off, we need the distance, or the amount of total change in the elevation of the pier over the period of time 715 to 2015. Now, originally the pier was built 1 meter above the ocean surface. So back in 1715, the pier was 1 meter above sea level. Now, in 2015, it's 1 meter below sea level. So that makes our total change 2 meters over a period of time of 300 years. We're going to divide that out, and that's going to give us 0.0067 meters per year. That's a rate, distance over time. Let's change that to centimeters per year. So I'm going to show you guys how to convert from one unit to another skill that you're going to need for this class. We want to make meters into centimeters, and I'm going to do that by multiplying times the ratio of meters to centimeters. In 1 meter, there are 100 centimeters. That's given in the problem, and something that you should just know in general because that comes up a lot. When we set it up this way, this is going to allow us to cross-cancel our meters, and then we're going to multiply across 0.0067 times 100. There's 2 zeros in 100, so that means that the decimal place is going to move 2 places to the right. Our final answer will be 0.67 centimeters per year. So that's our answer for part A. I should have made that a little bit clearer earlier. Let's put that over here. Part A. Okay. Now we're going to solve for part B. In this case, we're going to apply the rate at which sea level is rising to a practical problem where a person is interested in purchasing a pier. Now, at the moment, the pier is 50 centimeters above sea level. The owner has been told that if sea levels rise to the point where the pier is 30 centimeters above sea level, that's the danger zone because it can get flooded. Anything built on the pier can get flooded by storms or high tides. So that would give the owner 20 centimeters of room for sea level rise. So if the sea level rises 20 centimeters from where it is now, it will be within 30 centimeters of the base of the pier, which is what's been recommended against. So how much time will elapse before the pier and anything built on top of it is unsafe? So we have to once again go back to a rate problem, but we're going to rearrange the equation to solve for time instead of for rate. So rate is distance over time, but we want to solve for time. So we need to get time by itself, and I'm going to do that by rearranging the equation. I'm going to multiply time here so I can cancel it out. But whatever I do to one side, I need to do to the other as well. So T times R. If I rewrite the equation here, I have T times R equals D. Still want T by itself. So I'm going to divide by R, and whatever I do to one side, I need to do to the other. The R's will cancel out. And if I rewrite that equation again, I'm going to have T equals D over R. I'm going to plug in what I know. The distance is 20 centimeters. And my rate, I've already solved, that's up here, 0.67 centimeters per year. Divide that out, and that comes out to 29.9 years. These centimeters would cancel out. And so there you go.